Hello students, let's take a look at the following problem. An oil storage tank can be described as the volume generated by revolving the area bounded by y equals 5 divided by the quantity 16 plus x squared quantity closed raised to the 1/4 power, x equals 0, y equals 0, and x equals 2 about the x-axis. Find the volume of the tank in cubic meters, and we're going to round our answer to 4 decimal places. All right, so I think what makes this complicated is the fact that there's a lot of words involved, but more so the actual function, the main function that we're looking at, is an interesting shape that we don't really often look at. 5 divided by the quantity of 16 plus x squared raised to the 1/4 power. It's a rational function, but it doesn't have any asymptotes. And I've taken the liberty of actually inputting a graph from Desmos so that we can kind of see what this curve looks like. So let's add to that curve the other curves that bound the region that we're rotating, namely x equals 0, which is a vertical line at 0 along the x-axis, and actually coincides is the y-axis, right? Y equals 0, which is just our x-axis, and then x equals 2, which is another vertical line, this time when x is 2. So we have 4 curves, and the region that we're looking at to rotate is the region bounded by those 4 curves, 3 of which are lines and the other is a curve. And it's this blue region right here. And we are taking that region and creating a solid by rotating that region about the x-axis. What is that shape? What is that? What is that? Well, if you can imagine, right, flipping this around really fast, let's just kind of get a visual here. So we've got it coming around the other side, and if we add that dimension to it, right, it's kind of like a cylinder, but the sides are just a hair curved, right? So we've got this 3-dimensional shape, solid of revolution, going about our x-axis, and it's a solid, meaning it doesn't have any holes or gaps or anything like that. So this is just a solid shape. And we're in the section where we're talking about discs and washers. And so if we cut this solid perpendicular to the x-axis and pull that slice out, what is it? It's a solid disc, right? It's a disc. And we know that the volume of this disc, since we're cutting perpendicular to the x-axis, we give it a thickness, and we call that thickness dx. So the volume of an individual disk we know is pi r squared times that dx, right? That gives us the volume of this individual disk, where r is the radius for that disk. Let me put that r value back up into our picture. That r value is this distance right here, which is the distance from the x-axis up to our curve. 5 over the quantity of 16 plus x squared, quantity closed raised to the 1/4 power. So that curve is just our r value, right? Well, that makes it simple then to set up this integral. When we're getting a volume, we're adding up all those individual disks. So we're summing infinitely many disks. And what are we summing? We're summing the volume of each disk, which would be pi r squared. And because we're cutting perpendicular to the x-axis, the thickness is dx. And we note, again, we're cutting perpendicular to the x-axis. So we're adding up all these disks along the x-axis. And that helps us to define our limits of integration. So our region is bounded from x equals 0 to x equals 2, and so this right here is the integral that will give us the volume for this 3-dimensional solid. Now, we want to make that substitution because we said that r can be replaced with our rational function, so let me replace r with a rational function, and that means we have a volume from 0 to 2 of pi times that rational function, 5 divided by the quantity 16 plus x squared raised to the 1/4 power, And that's our r value, so that all has to get squared and then integrated with respect to x. Let me clean this up just a hair. So if we clean this up, let's see. On top, we have 5 squared times pi. So that's going to give me a 25 pi, and I like to pull those constants out right away. That's going to leave 1 over, and now, again, we're going to take that bottom quantity and square it. So when you have an exponent raised to an exponent, we multiply those exponents. That's going to give us 2/4. 2 times 1/4 is 2/4. Or, if you simplify down, that would go down to 16 plus x squared quantity raised to the 2/4, or, sorry about that, 2/4 or 1/2 power, right, if you simplify it down. And I'll go one more step for the simple fact of pattern recognition. How are we going to integrate this function right here? The integral from 0 to 2 of 1 over the square root of 16 plus x squared dx. Notice there's no x variable on top, so substitution isn't going to help. What is that method that's going to help us here? Does anything ring a bell when we have a quantity squared plus another quantity squared? Or what if I wrote this as a squared plus x squared, where a is 4? Any thoughts? Yeah, trig substitution. So trig substitution, remember, is this quick, wonderful way of integrating functions that have like a Pythagorean formula in it. So this is trig substitution. And specifically, when you have a plus in here with a squared plus x squared, the trig substitution that you want to use is x equals a tan theta. So let's go ahead and let's work out this integral. But this integral right here is all we need to get the volume. So looking at our integral, we're going to make our trig substitution. And I said that x equals, so we'll write it out here, x equals a tan theta. But our a value is just 4 because 4 squared is 16. And that means that our derivative with respect to x is going to be 4 times the derivative of tangent, which is secant squared theta d theta. Now, as we go forward, this is a definite integral. It has limits, and those limit values pertain to the x-axis. So I'm just going to write next to it x equals 2, x equals 0. We can either at this point choose to go ahead and make a substitution and change those limits to be theta limits, but we might need to do a little bit more after that, so we might have to do and change them again and again. Sometimes when we're doing trig substitutions, it's just as easy to leave the limits alone and then plug them back in at the very end. So I think that's the least confusing way with students, and I think that's the way I'm going to explain it. So I'm going to simply take this integral and leave those limits on there, but I'm going to denote that they have to deal with my x variable, so I don't forget that. So 2 has to be x, 0 is going to be x when we get back to x's, but I am going to make a substitution now. I'm going to replace x with the expression 4 tan theta, and I'm going to replace dx with the expression 4 secant squared d theta. And when I do that, I get 1 over the square root of 16 plus, and in place of x, I'm putting 4 tangent theta. So when I square it, it should give me 16 tan squared theta. The dx is getting replaced with 4 secant squared theta d theta. And continuing on, what do we do when we have a trig substitution? Well, the first thing we do is try and simplify what's under that square root. And just remembering, I'm going to go rather quickly through this because this is kind of a review. We factor out that 16. We rewrite that 1 plus tangent squared using our fundamental identity as secant squared theta. And so what does that give us? That gives us that the volume for this solid of revolution from 0 being x to 2 being x, 1 over, and what's on the bottom? The square root of 16, which is just 4, the square root of secant squared, which is just secant theta, times 4 secant squared theta d theta. Now we're getting somewhere. Alrighty, what can we do to simplify this integral? Well, we can cancel the 4's. We can cancel a secant theta. And so really the volume is just 25 pi. Integral from 0 to 2, both of those being x values, of just simply secant theta d theta. Now this is an integral that comes from Calc 1. It's either something you memorize, or something you look up, or something that you generate by multiplying numerator and denominator by the secant theta plus tangent theta. But in any case, however you like to do this, I'm just going to go ahead, because I've done this a million times, I'm just going to write down what it is, that the antiderivative of secant is the natural log of secant theta plus tangent theta. And again, that comes from my Calculus 1 knowledge. And if you want any help with that step or want to know a little bit in between, simply email me and I'm happy to show you how it goes to that step right there. We're going from 0 being x to 2 being, when 2 is x is 2. And that's important. Our limits are based on us having x as our variable, not theta. And how do we go from theta back to x again? We use a right triangle. At least that's the easiest way and the way that I like to do it. And that right triangle gets defined by our original substitution. X divided by 4 is our tangent for theta. So if you set up a right triangle with the angle of theta, tangent is opposite over adjacent, so tangent is x over 4, and then using Pythagorean theorem, that makes our hypotenuse 16 plus x squared. And there's always that trick that when you use your hypotenuse, that quantity should be appearing, or some fraction of it should be appearing in our original expression, and it does, and so everything looks really good. We're going to make our two substitutions. Based on this triangle, what is secant? Secant is hypotenuse over adjacent, and tangent, we just said, is opposite over adjacent. So let's make those substitutions, and that tells me that my volume is 25 pi times the natural log of the absolute value of hypotenuse, 16 plus x squared, over adjacent, which is 4, plus tangent, which is x, divided by 4. And now we're back with the variable x, and we can substitute in our limits to find the final answer. That means our volume is 25 pi times the natural log of, and if we put 2 back in there, 2 squared is 4, so that's going to give us the square root of 20 over 4 plus 2 over 4 minus the natural log of the square root of 16 over 4 plus 0 over 4. If we clean up that second expression a little bit, we have square root of 16, which is 4 over 4, and plus 0, so that's actually just 1. And the natural log of 1 is just the value 0, right? The natural log of 1 is just 0. And so that simply means that the volume of this solid of revolution is 25 pi times the natural log of the square root of 20 plus 2 over 4. And I can put that together if I want to. I can do some canceling. Do I want to be tricky about this and do some canceling? Well, let me write down what it is first. We can put a lot of things together, but if you actually went one more step and wanted to simplify square root of 20 as 2 square root 5, make some cancellations, you should get, and see if this makes sense. So I'm just going to put that this is our answer, or if you want to go down and simplify a little more because you love math and you love to simplify things, you could transfer it down to be 2 square root 5 over 4 plus 2 over 4. Make another cancellation, right? And so we could get that the volume 2, if we canceled down, would be 25 pi times the natural log of the square root of 5 plus 2 over 2. And that's it. Cubic units, of course, at the back end. Not too bad. Oh, but the answer did say, so actually I probably wasted a little bit of extra time because it did say to go ahead and take that expression and round it to the nearest 4 decimal places. So let's put that into decimals. Oh, wait, and as I'm looking at it, I see one little mistake I made here, right? This should be square root 5 plus 1. See that goof right away, so let's edit that before we stick it in decimals. Catch that right there. So we're putting in 25 pi times the natural log of the square root of 5 plus 1 divided by 2. And that gives us approximately 37.7942883607. Rounded to the nearest 4 decimal places would be 37.7943 cubic units. I'm not sure. I hope that my open math would take the exact answer versus the approximation. But you'll have to check and see, okay? Either way. Whew. Okay, well, if you guys do have any questions about this problem, again, the hardest part, I think, is actually evaluating this time instead of the setup. But if you do have any questions, don't hesitate to reach out.